Gravity as the gradient of the inertia field perceived by an external body, a field-theoretic hypothesis. Abstract. This work extends the foundational ideas introduced in 2 previous studies. Resolving the inertia principle inconsistency by introducing the concept of the field of inertia, and inertia as an emergent pressure gradient from the quantum vacuum. A field of inertia-theoretic hypothesis. Building upon these concepts, we examine the structural and behavioral similarities between the classical gravitational field and the inertia field, particularly emphasizing the inverse square nature and radial symmetry. We then investigate the local interaction between a physical body and Earth's inertia field, proposing a novel interpretation of gravity as the body's experience of the spatial anisotropy of an external inertia field. The work culminates in the proposition of a general equivalence between gravity and the gradient of an inertia field, unifying both under a common field-theoretic framework. 1. Introduction. In earlier work, we resolved the historical inconsistency in the principle of inertia by proposing the existence of an underlying inertia field that interacts with all physical bodies. This field was then modeled as an emergent pressure gradient from the quantum vacuum, a concept that allowed inertia to be viewed not as a mere resistance to acceleration but as a dynamic interaction with the vacuum structure. In the present paper, we extend this approach to gravity. Specifically, we suggest that gravity is the relative perception of the anisotropy of an external inertia field, typically that of a large mass such as the Earth. This leads to a field-theoretic equivalence between gravity and inertia. 2. Analogies between Newtonian gravity and the inertia field. Let us consider the characteristics of the gravitational field in Newtonian mechanics. Radial symmetry. Inverse square law decay. Proportionality to mass. These same properties can be derived naturally from the structure of the proposed inertia field. The field is isotropic around a massive object. Its influence decreases proportionally to the inverse square of the distance from the center. The net effect on another body depends on the body's own mass. Thus, we identify structural and functional similarities between gravity and the field of inertia. 3. Local analysis of Earth's inertia field. From the perspective of a physical body placed near Earth, Earth's global isotropic inertia field becomes locally anisotropic. The pressure exerted by this field on the body's constituent particles is no longer uniform in all directions. This net anisotropy translates into a force directed toward Earth's center. The total force experienced by the body is proportional to its mass and to the spatial gradient of the field intensity. The negative sign indicates that the force is attractive. 4. Thought experiment. Immersion of a body into Earth's inertia field. We consider a physical body in deep space, far from any massive object. In this case, the body's inertia field is isotropic and experiences no external anisotropy, resulting in no net force. Now, immerse this body near Earth, within the reach of Earth's inertia field. The surrounding field is now directionally biased, stronger from one side. The body's material elements are subjected to unequal pressure from different directions, resulting in a net force. This is perceived as gravitational acceleration. This reasoning leads to the conclusion: gravity can be interpreted as the manifestation of local anisotropy in the field of inertia, as experienced by an external body. 5. General principle and elegant formulation. We propose the following equivalence principle. Inertia field, gravity field. This reasoning leads to the following compact and elegant field equation. This equation unifies gravity and inertia under a single conceptual framework. Gravity is the gradient of the inertia field intensity. This formulation not only explains the proportionality between mass and weight but also bridges the gap between quantum vacuum pressure models and gravitational phenomena. 6. Conclusion. We have shown that gravity, traditionally understood as an attractive force between masses, can be reinterpreted as the local anisotropy of an inertia field generated by massive objects and perceived by an external body. The resulting net pressure on a body immersed in this field produces acceleration that is indistinguishable from gravitational acceleration. Gravity can therefore be interpreted as the manifestation of local anisotropy in the field of inertia, as experienced by an external body. This field-theoretic framework naturally recovers Newtonian gravity while providing a deeper explanatory model rooted in quantum vacuum interaction. From this perspective, both inertial mass and gravitational mass arise from the same underlying mechanism: the body's interaction with the structured pressure field of virtual photons in the quantum vacuum. Hence, inertia and gravity are not two distinct phenomena, but two aspects of the same emergent phenomenon, perceived differently depending on whether the field is self-experienced or externally encountered. This unified interpretation not only explains the equivalence between inertial and gravitational mass, but also opens the way toward a field-based reformulation of general relativity grounded in the properties of the quantum vacuum.